In 1922, in the hills outside San Francisco, a 10-year-old boy sat down to take a test. He was not told what the test was for. He was simply asked to solve puzzles, answer questions, and think as quickly as he could. Somewhere in a Stanford office, a psychologist was scoring his answers. Against a formula, one meant to reveal something permanent about the boy's mind. The number came back too low. He did not qualify. Around the same time, in Palo Alto, another young boy took a similar test, and he was rejected too. Both boys would go on to reshape modern physics. Both would win the Nobel Prize. And neither one was ever considered a genius, according to the very test built to find geniuses. To understand how that happened, you have to go back to where the modern idea of a fixed intelligence score actually began, and to the man who never intended it to work that way at all. In 1904, the French Minister of Education gave psychologist Alfred Binet a narrow, practical assignment: find a way to identify school children who were struggling so they could get extra help. Working with his collaborator, Théodore Simon, Binet built the first practical intelligence test in 1905. It introduced something new, the idea of a mental age, a way of comparing a child's reasoning to what was typical for their years. Binet was clear about what his test could and could not do. He warned against what he called the brutal pessimism of treating a child's intelligence as a fixed quantity.
Something stamped in at birth and unchangeable for life. His tool was meant to open doors for children who needed support,
not to sort human worth into a single number. That caution did not survive contact with the century that followed. Within years, Binet's test was reshaped by movements he never endorsed, used to sort and rank rather than to help. In the United States, psychologist Lewis Terman adapted the scale into the Stanford Binet test and, unlike Binet, believed deeply in fixed, inheritable intelligence. In 1921, Terman launched an ambitious project: find the smartest children in California, follow them for the rest of their lives, and prove that a high IQ meant a life of extraordinary achievement. He called it the genetic studies of genius. His subjects, nicknamed the termites, were selected for IQ scores above 135, sometimes 140. Terman was confident he had assembled the future elite of American science, letters, and industry. Decades passed. The termites grew up. Many did well. Some became doctors, professors, engineers. But by his own account, years into the study, Terman had to admit something uncomfortable. Some of his high IQ subjects had ended up in what he called humble occupations, ordinary working lives, no different from their less gifted peers. Terman himself eventually concluded that intellect and achievement were far from perfectly correlated. And then there was the detail that would haunt the study for decades. During the screening process, 2 children were tested, evaluated, and turned away. Their scores fell just short of Terman's cutoff. Their names were William Shockley and Luis Alvarez. Shockley would go on to co-invent the transistor, the device at the foundation of every modern computer, and win the Nobel Prize in Physics in 1956. Alvarez would help build the hydrogen bubble chamber that transformed particle physics, and win his own Nobel Prize in 1968. Not one child admitted into Terman's hand-picked group of geniuses ever won a Nobel Prize at all. It is tempting to read this as proof that IQ tests are worthless. The more careful truth is subtler and more useful. Later analysis found that Terman's cutoff was simply too high relative to how common IQ scores in the 120s actually are among real Nobel laureates. The test was not measuring nothing. It was measuring one narrow slice of a much larger picture, and mistaking that slice for the whole. So if a single number cannot predict who becomes a Feynman, a Shockley, or an Alvarez, what can? Richard Feynman is often cited as living proof that genius does not require a high IQ, a solid but unremarkable number. The claim is repeated constantly, but it rests on a single adolescent test result, reported secondhand by Feynman and his sister at different points, never independently verified. Whatever the real number was, Feynman himself seemed to treat the test as beside the point. What mattered was not the score. It was what he did with his mind afterward, the years spent tearing apart equations and rebuilding them from first principles until he understood them completely. That habit, not a number on a childhood form, points to where real cognitive change happens. Consider what neuroscientists found when they studied London's taxi drivers. To earn a license, these drivers must memorize roughly 25,000 streets, a task so demanding it takes years to complete.
Researcher Eleanor Maguire scanned their brains and found something remarkable. The posterior hippocampus, the brain region tied to memory and navigation, was measurably larger in taxi drivers than in people of similar age and background.
The longer someone had driven, the larger it tended to be. Follow-up studies went further, tracking trainees over time, and finding that this brain region actually grew during training, but only in those who went on to pass the test. London bus drivers, who drive just as many hours but along fixed, repetitive routes, showed no such growth at all. The difference was not luck. It was the specific, demanding mental work of building and constantly updating a complex internal map. The same pattern shows up far from London's streets, on a chessboard. Researchers studying chess masters found their advantage was not a superior short-term memory. It was pattern recognition, built from experience. Masters had stored tens of thousands of meaningful piece arrangements in long-term memory, letting them recognize a board position and its best moves almost instantly. Remove the meaningful patterns, replace them with randomly scattered pieces, and the master's advantage nearly disappeared. Their edge was not raw brain power. It was a library built one game at a time. Psychologist Anders Ericsson found something similar studying musicians, athletes, and other high performers. He called it deliberate practice, breaking a skill into specific parts, drilling those parts with focused effort, and using feedback to adjust before the next attempt.
It is not the same as simply putting in hours.
It is structured, uncomfortable, and aimed directly at your weakest points.
Later research added an important caveat. Practice alone does not explain everything, accounting for only a modest share of the differences between top performers.
But within that share lies something genuinely within anyone's control. None of this means intelligence is infinitely malleable, or that anyone can become a Nobel laureate with enough flashcards. What the evidence actually supports is narrower and, in its own way, more useful. The specific mental structures behind expert performance, the patterns, the navigational maps, the deeply practiced skills, are built, not simply inherited. They grow the way a taxi driver's hippocampus grows, gradually, through demanding, repeated use. Picture those two boys again, sitting in their classrooms in 1922.
Answering questions on a form neither of them would remember years later.
The paper in front of them held a number.
It did not hold a ceiling.